In our effort to solve the problem of finding the center of mass, we're going to simplify the problem into a two-dimensional one. In other words, we're going to look at points of mass along a line, and we're going to in order to find the lines of balance in the more complicated situation, we're going to need some preliminary results about rotations. Now, children on a seesaw learn by experience that a lighter child can balance a heavier one by sitting farther from the fulcrum or pivot point. This is because the tendency for an object to produce rotation is proportional not only to its mass but also to the distance between the object and the fulcrum. We're going to imagine that this teeter-totter is running along the x-axis. This person on the left is going to be called mass 2. We're going to imagine that the person is actually a point of mass, and that mass is located at the point x2 on the x-axis. This person on the right is the point m1, mass 1. Imagining that all of the mass of that person is located at one single point on the line, and that point on the number line is x1. Then the fulcrum or pivot point is located on the x-axis at the x value a. The distance between the fulcrum and mass 1 is x1 minus a. The distance between the fulcrum and mass 2 is going to be x2 minus a. Now we're going to define the moment of mass 2 about a to be m2, the value of the mass, times x2 minus a. This is going to be a negative value because of the fact that x2 minus a is negative, and it also reflects the fact that we're causing a counterclockwise rotation. And the moment of m1 about a is defined to be m1 times x1 minus a, which is positive, causing a clockwise rotation. Now let's consider what's going to happen when we add the quantity m2 times x2 minus a plus the quantity m1 times x1 minus a. Well, in this diagram, notice that m2 is a smaller person with less mass. But to compensate for that, we have a larger distance from that person to the pivot point A. So when we multiply the smaller number for the mass times the larger number for the distance, we're going to get some, and when I say larger, I mean in magnitude, we're going to get some negative number. Now this person on the right, this person is going to have a larger mass, and we're going to multiply that larger number times a smaller distance. Now if they're situated appropriately, the magnitude of the number that we get, the positive number, m1 times the distance here, is going to be the same as the magnitude of this negative number. If that's the case, then these are going to cancel each other out when we add them together. So if this is equal to 0, then what we have is equilibrium. In fact, in general, if you add up all of the moments of any mass points along this line, then if they add up to 0, you're going to have equilibrium. If we have a larger magnitude on the negative side, then it's going to tip to the left in the counterclockwise direction. And if we have more magnitude on the right-hand side, then it's going to tip to the right. The preceding ideas can be extended to masses distributed in two-dimensional space. If we imagine the xy plane to be a weightless sheet supporting a mass m located at some point xy in the plane. then the tendency for this mass M to produce a rotation of the sheet about the line x equals a here in red is the moment of M about x equals a, which is equal to M times the distance between x and a. Similarly, the tendency for the mass to produce a rotation around this line, y equals c, would be called the moment of M about the line y equals c, which would be equal to M times y minus c. If the masses are distributed throughout the xy plane, then the plane will balance on a knife edge along x equals a or y equals c, depending on the scenario. Now let's consider breaking a lamina up into rectangles again. This time, let's suppose that the center of mass is located at x bar, y bar, and so we know that this lamina would balance on a knife's edge that ran beneath the lines x equals x bar and y equals y bar. We have that the moment of some point x sub k star y sub k star about the line x equals x bar would be the mass at that point times the difference between x sub k star and x bar. That would be this quantity over here. Similarly, the moment of x sub k star, y sub k star about y equals y bar is going to be the mass delta m sub k, the mass at that point, times the difference between y sub k star and y bar. Now, remember, the masses are equally distributed in the sense that this lamina would balance on this line y equals y bar, and it would also balance on the line x equals x bar. So what that means is, if I take all of the different points, x sub k star, y sub k star, and their masses, and create their moments, and add them up, then they would be in equilibrium, and so their sum would be 0. So that gives us that the sum from k equals 1 to n of x sub k star minus x bar times delta m sub k, which we know, by the way, that the mass delta m sub k is the density times the area. So that would equal k equals 1 to n of x sub k star minus x bar times the delta of xy, the density at xy. Actually, I should say x sub k star, y sub k star, the density at that point, times delta a sub k. This is approximately 0. Now, as n goes to infinity, the number of rectangles going to infinity, then the size of the rectangles would go to 0, and as previously, the error in this approximation would also tend to approach 0. So we could say that it's reasonable to see how it would turn out that the limit as n goes to positive infinity of this sum, k equals 1 to n, of x sub k star minus x bar times delta at x sub k star, y sub k star times delta a sub k would equal 0. But notice that this quantity is the double integral over r of x minus x bar times the density function dA, and so we have that that is equal to 0. Now, separating this into the difference of two integrals, one the double integral of x times the density function, the other negative x bar times the density function, and taking into consideration that x bar is a constant which can be moved out of the integral, we would have the double integral over r of x times the density function dA minus x bar over the region r times the integral over the region r rather of the density function dA equals 0. But we could rearrange this by moving it over to the other side, which would give us that the double integral of x times the density function is equal to x bar times the double integral of the density function alone. And remember, our goal here is to figure out the coordinates x bar, y bar. Well, right now we have an equation that we can easily move the integral, divide by the integral, and get x bar. So now we have x bar is equal to the double integral over r times x times the density function dA divided by the double integral over r of just the density function by itself dA. And you can do all of the same steps with the to obtain the formula for y bar. So it's going to be the double integral over r of y times the density function dA divided by the double integral over r of just the density function dA. And so we have a way here using the density function to find the center of mass. A couple of things to mention about this formula for x bar, y bar. First of all, notice that the denominator is really the mass of the lamina. And so a lot of times we'll actually just call that m. And then we give a special name to this value in the numerator. We're going to call that m sub y, or the first moment of the lamina about the y-axis. And this numerator we're going to call m sub x, or the first moment of the lamina about the x-axis. So here are a couple of ways to write these two formulas. So let's take a look at an example where we find the center of mass for the lamina that we looked at before, with density function delta of xy equals y, and bounded by y equals sine of x, x equals 0, y equals 0, and x equals pi. We're going to start by drawing our region R as we did before, from 0 to pi sine of x. Here's our lamina. And then the first thing we're going to do is find the mass of the lamina. Well, we did that in a previous video segment. We found the mass of the lamina. M was equal to pi over 4. Next we need to find m sub y, which is the double integral over r of x times delta of xy dA, which is going to be the integral from 0 to pi. That would be our x bounds, so dx is on the outside. The integral from 0 to sine of x, these are our y bounds, bottom to top, dy of x times the density function y. Integrating with respect to y then, we're going to have the integral from 0 to pi of xy squared over 2, and substituting in sine of x and 0, we're just going to be left with x sine squared x over 2 dy, or rather dx. Now let's go ahead and replace sine squared with 1 minus cosine 2x over 2. So we're going to have the integral from 0 to pi of x over 2 times 1 minus cosine 2x over 2 dx. So this is going to be equal to 1/4 of the integral from 0 to pi of x minus x cosine 2x dx. Now, after you work this out, you're going to find that you're going to get pi over 2 or actually, excuse me, that's going to be pi squared over 8. Okay, so what we're going to have then is our x bar is going to be equal to my over m, which is going to be pi squared over 8 divided by pi over 4, which is going to be equal to pi over 2. Now, one of the reasons why I'm skipping all of the work here is because it's kind of a waste of our time, being as we can use the symmetry of both the lamina and its density function in order to see that the x-coordinate of the center of mass would have to be at pi over 2. And what I mean by that is, do you remember how the density function, when we looked at it previously in a different video segment, we talked about how this is a density function which is the same along every horizontal line. It's the same at every point along a given horizontal line. It's increasing as we look at horizontal lines with larger and larger y values because the density function is equal to the y value. So we said it's more dense at the top, less dense at the bottom. But from side to side, it actually has the same density. And it has the same size because this region is symmetric around pi over 2. So it makes sense that we would get x bar equals pi over 2. And it would be just fine to use that kind of reasoning, the symmetry of the lamina along with the density function, to conclude that x bar was equal to pi over 2. Next we would go ahead and find m sub x, which is the double integral over r of y dxy dA, or in this case the double integral over r of y squared dA. So that's going to be the integral from 0 to pi of the integral from 0 to sine x of y squared dy dx, which is going to give us the integral from 0 to pi of sine cubed of x over 3 dx. And then applying the end paper integral formulas here, we would get, and plugging in pi and 0, we would get 4/9, which means that mx is equal to 4/9 divided by pi over 4. And that means that y bar is equal to m sub x divided by pi over 4 equals 4/9 divided by pi over 4, which is equal to 16 over 9 pi. So our center of gravity will be located at pi over 2, 16 over 9 pi.